Okay, it's about a minute after, so I think we'll get started here. Good afternoon, and welcome to today's webinar, Optimized Test and Antenna Connectors for Millimeter Wave 5G, sponsored by the following Hirose franchise distributors, DigiKey, Mouser, Future Electronics, and Highland Electronics, who are all authorized to sell the portfolio of Hirose Interconnect products. I'm Bill Kysiak, and I'll be your moderator today. We have a few brief announcements before we begin. First, this webinar is designed to be interactive, and we encourage participation in the Q&A session that will take place at the end of our presentation. You can submit questions at any time in the chat area. Please note that we'll get to as many of the questions as we can in the time left at the end of the program. However, if we don't get to your question today, someone will get back to you after the program has ended. If you want to view in full screen mode, click on the red tab on the right side of your screen. And now for today's presentation, Optimized Test and Antenna Connectors for Millimeter Wave. Discussing today's topic is Mark Waring, Strategic Account Manager supporting Hirose's RF, 5G, and consumer solutions. Mark is a graduate of San Diego State with a Bachelor of Science in Physics and an MBA from Pepperdine University. It's with great pleasure I now turn this special session over to Mark. Mark, take it away.
Okay, I'm sharing my screen.
Looks good, Mark. Looks like you're ready to go.
Perfect. All right, thanks. Thanks, Bill, and thanks, everybody, for taking your time to join today. I'm going to share a quick overview. We're targeting just half an hour, and that's going to include time for any questions at the end, roughly divided into three parts. First, I'm briefly going to introduce our leading-edge portfolio of RF products, and specifically millimeter wave test and measurement environment types of solutions. Next, I'll discuss our in-house signal integrity and end system optimization engineering capabilities. And finally, we're going to take a quick look at bringing microconnectors into this millimeter wave 5G frequency domain for RF transmission. And I will repeat, as Bill mentioned, definitely please share any questions you might have in the chat box. We're not going to interrupt the webinar for those, but certainly include those, and we'll be happy to leave time to address those at the end. Hirose, if you don't know much about us, is best known in the technology industry as a leader in microconnector solutions for various consumer electronic products. This is just an example of a smartphone and how a lot of our different devices would fit into that type of product. At Hirose, we're continually developing literally best of class, literally world's smallest form factor, ruggedized and optimized connectors for transmitting digital signals, power, and analog signals throughout your smartphone, your earbuds, your smart speakers, home devices, etc., etc. These types of connectors that we focus a lot of our attention on include what we call micro board-to-board connectors. A micro board-to-board, although probably more often they're micro board to FPC would be what one of the elements of the connector pair would be mated to. Another family over here on the right would be the world's lowest profile zero insertion force, or ZIF connectors, which is another way of connecting to a flexible printed circuit cable. Back on the left, we do a big family of various board-to-wire solutions, from very small to actually very large, for even EV type applications, for example, or renewable energy applications, down to very small micro type connectors for CE products, as shown here. We pioneered the micro-coax solutions with our various FL series, which I will discuss in a little bit more detail in just a couple slides. And we do I/O connectors, USB Type-C, for example. But we also have a more focused portfolio of RF solutions. And some of those core families of those solutions are shown here. I'm not going to address the bottom row today, other than to quickly mention the fact that we do leverage our leading ZIF and board-to-wire capabilities to offer some ganged micro-coax solutions down here in the lower left. We also offer both SMA and professional video BNC 75 ohm series for broadcasting purposes primarily. We do push-on MMCX and SMP, SMPM style RF connectors. We also have some fairly unique hybrid, what we call coax bridge solutions for transitioning a panel-mounted BNC or SMA connection to a much smaller board space solution of a micro coax. So I will quickly mention what we're offering today in the FL series. Hirose actually pioneered the RF microcoax solutions, being the very first to market with our own U.FL branded product over 30 years ago, here on the left, which is today a de facto industry standard form factor. Shown to the right are examples of our own progression since then, introducing smaller form factor, higher frequency solutions. And most recently, we've launched our C.FL series, which takes these micro-coax solutions into the millimeter wave domain for the very first time, with signal integrity performance rated all the way up to 30 gigahertz. At these frequencies, the system, the cabling, the PCB optimization all become more critical. And I'm going to discuss our services and what value we can bring to you in that area as well in just a few slides. But just as an example of a little more detail of what these connectors look like, this is one of our more popular X.FL series. It comes in at under 1 millimeter in total height, including the attached plug and cable, and only 2 millimeters in width in both X and Y. So this is small enough to be used in almost any consumer electronics product, as well as larger form factors. It allows multiple connections, even with limited circuit board space. And just to note, this is an actual more recent introduction of a variant of the X.FL called the X.FL-V, which applies a little bit better shielding primarily on the plug, which is what we call the part at the end of the cable, to push that frequency capability from a typical 6 gigahertz up to 12 gigahertz, and can be as high as 18 gigahertz under certain conditions. Here we are looking at what would be typical SI data for any of these types of RF connectors, things like VSWR, insertion loss. It also comes with a tactile click function, which ensures mating, which can be very important in a high volume manual assembly line. Again, the very newest product, however, is the C.FL. It maintains that same reduced form factor, while through receptacle and plug optimization pushes that frequency performance dramatically higher, in this case all the way to 30 gigahertz for true 5G millimeter wave application capabilities. The C.FL is a new option to consider, therefore, when running extended lengths of high frequency RF through small or demanding routing paths. Here on the right, we see looking at the VSWR, which would be the primary signal integrity factor of interest to an engineer. And you can see as we push out beyond the previous typical 6 gigahertz range, the divergence of the performance of the C.FL versus even one of our better performing previous generation products. So it's a really different animal altogether, and pushes by a factor of 3 or 4 the frequency capabilities of these types of products. More data on the signal integrity performance is available, as well as 2D and 3D models are available for these connectors, as well as some standard PCB design optimization guidance are all available. And you can ping us if you're not sure how to find that on our website, and we can help you out. Now, one more thing I think is worth a very quick mention is our leading RF switch family, the MS switches. And the reason they're worth mentioning is simply because they're so ubiquitous, and they show up on very frequently on everything from early engineering test boards to eval boards, to reference kits, all the way to high volume final products, including tier 1 smartphone OEMs who are investing BOM space and cost to include multiple RF switches like these on their final products. And the reason they do that investment is because of the benefit. These devices allow in situ rerouting of analog RF signals by temporarily depressing the switching element, which in turn allows partial circuit performance validation at any manufacturing stage, from design all the way through high volume assembly line stages. Their small size keeps the board space investment to a minimum, with over here on the right, the latest MS-190 measuring less than 1.5 millimeters to a side and only 68 hundredths of a millimeter in height. So how do you use these guys? Well, these are what we call the probes, which are used to actually depress the center of those switches to divert the current. And on the top are 2 examples of probes that are designed for use as fixed-mounted, automation-ready solutions. So these could be used in an automated assembly line. These come with full 3D floating capability, meaning the tip, if you hold it in your hand and play with it, actually jiggles in X, Y, and Z direction. And that prevents damage from continually depressing these devices with some variable tolerances in your system. And on the bottom is a handheld version of the same type of probe for use in a laboratory environment. This can come with some various forms of locking mechanisms as well to help it stay attached to your receptacle on the PCB as you're doing whatever evaluation or experiment you may be doing in a laboratory environment. And back to our overview, let's look at one of the focus areas for today's talk, which are the millimeter wave optimized test and measurement solutions. Who uses these types of connectors? Any engineer who needs to access high frequency RF signals from a new circuit design, for example, from an RFIC output, from an entire RF subsystem assembly, including definitely antenna related signal analysis efforts. These connectors often may be an integral part of a larger circuit, of a component test board, or of a full subsystem, or even end product design. They're connecting to test equipment in one form or another. Like most elements of any technology hardware today, test and measurement solutions are also seeing a gradual evolution towards higher frequency capabilities. Our own Hirose lineup, which does hone largely to the accepted industry usage and form factors, includes push-on options in our SMP and SMPM devices, but focuses more on the mainstream lab and early engineering board engineers who prefer to have a screw-on connection for stability. And these 3 families are shown here, with the current core of these, including from the left, are 2.92 millimeter or K-band connectors rated up to 40 gigahertz. Our 2.4 millimeter series rated up to 50 gigahertz, and the 1.85 millimeter series or V-band connectors, which are rated up to 67 gigahertz, where we're seeing more customers migrate towards today. The connectors that are mounted on PCBs are called receptacles. And we provide both vertically mounted options, here shown here, in each of those different flavors, 2.92, 2.4, and 1.85, as well as horizontal mount, or often referred to as edge launch options, shown here on the right. The vertical mount devices are available in 2 different varieties. One is a strip line variety, and one is a microstrip option. And I'll explain the difference between those in just a second. But these connectors are used anywhere a reliable, easily accessible connection to board circuits is needed to test or transmit high-frequency RF signals to another off-board circuit element, or simply to an external piece of test equipment, such as I showed on the previous slide, a vector network analyzer or an oscilloscope. Now, to clarify the difference between those two vertical types I mentioned, strip line versus microstrip. It's hard to distinguish them just from the overall connector appearance, but if we take a little closer look, we can easily describe the difference between the two. For strip line, this stub, which is this little element here, the actual contact that's making contact with your PCB. In the case of the strip line version, that stub extends slightly above the plane of the PCB connection, or interface layer between the connector and PCB. And it does so in order to be inserted into a plated via connected to an embedded trace on an inner PCB layer, which may be embedded between two ground planes, for example. The microstrip version, which isn't shown here, but in that case, it's easy to describe. The stub would actually end flush with the mounting surface of the connector itself. And in that case, it's tuned to mate to a surface trace on the top of the PCB trace. So strip line is for essentially for an embedded trace, and microstrip would be for a surface trace. Finally, if we freeze an image from that last video, it's also worth noting, just to point out, that surface trace or microstrip version also requires a groove in the overall connector in order for your surface trace on your PCB to reach the embedded contact in the middle of the connector without making contact with the grounded connector itself. So that's an easier way to actually identify the difference between these connectors if you have them in your lab. If there's a groove on the bottom, it's going to be intended for a surface mount or microstrip version of the device. We also provide a full line of accessories for these millimeter wave test and measurement connectors, adapters shown here to go from one size connector or one series to another, 2.92 to 2.4, for example. Terminators for capping unused receptacles on your test boards with a matching impedance load. Attenuators, if you're in an environment where you need to mitigate the transmitted power levels available for each of the families, and available with a variety of dB attenuation levels in increments of 1 dB from 0 to 10, and then jumping to a 20 dB option as well. And finally, a testing environment is only as good as the weakest link. And Hirose has recently introduced our own in-house OEM branded cables, starting with the HK or 2.92 series shown here. These offer rated performance levels in line with our leading receptacles. We will be adding 2.4 millimeter cables later this year, so offering a little bit more comprehensive system solution option. And finally, this is just a little cheat sheet because I get frustrated looking at even our own part numbers, and I know people who have to work through different components might have the same. So this just shows all the different part numbers in one slide. Also, the little suffixes at the end. In our case, these denote for the millimeter wave connectors different length mating screws, which come with these receptacles to mount to the PCB boards. So let's move on and talk about actual simulation and modeling of these types of solutions. Successful designs in millimeter wave domains typically require not only precision in hardware selection and components, but also some degree of performance simulation itself, not only at the component level, but even more importantly at the subsystem level. So let's discuss some of those capabilities and take a look at where Hirose adds value. We have a large sales and engineering office here in the heart of Silicon Valley, where I'm located, which includes our own signal integrity engineering team, which serves customers throughout the country. Our engineering team is focused on high-speed design projects, both digital, such as, for example, massive server back-end interconnect solutions, and analog designs, working on largely millimeter wave domain, component, board, and subsystem projects with various customers. And it is all about the system, is one way I've heard it put, about the need to consider each element of an RF millimeter wave design effort. And this starts with the PCB substrate itself. Our SI engineering team offers standard PCB design optimization guidance, but they can also dive deep into a specific customer requirements, design, and questions. This can be as obvious as offering input on ground via locations and anti-pad layouts, spacing, and dimensions, but can go further and address and analyze additional features, including side plating effects on the edge of a PC board, stitching via locations for waveguide solutions, glass weave style effects, again, a PCB related factor, even surface roughness of copper foil layers, via stub effects, not the stub on the connector itself, but stubs that may be legacy stubs and have effects on the actual PCB design, and PCB materials. PCB stack-ups, absolutely something that we get involved in looking at together with customers. In fact, here's a more detailed view of a type of simulation at work for a specific millimeter wave test connector, analyzing, in this case, impedance matching through TDR, TIR, as well as VSWR, and looking to optimize that performance. Again, not just for the connector, not just for the PCB, but for the connection, for the combination of the two. And here's another example of the same kind of effort, just a little bit different view of the types of CAD tools that are used in this case. And over on the right is a little bit clearer example of the importance and the benefit of going through these steps. The blue, red, and black lines here on the right graphs are examples of iterations of design optimizations with an original unoptimized VSWR and reflectivity performance shown in blue, and the obvious improvement in the performance of both those factors through successive iterations of optimization. So again, nothing was changed with the component itself. It was just the mitigation of those effects of the connector together with the PCB layout and construction that allows a very significant improvement in the overall subsystem performance in this case. Whoops, oh, there we go. I need to click on that. And finally, here's a recorded example of an actual PCB footprint model being generated in an HFSS environment. This one was done here locally by our San Jose-based engineering team, but they also frequently coordinate directly with our various product design and engineering teams, both at our Yokohama, Japan design headquarters, as well as at our large Korea Design Center location. Of course, this exercise is simply building the model, selecting patterns, stack-ups, and via placements. This would be followed by some actual SI performance simulation results for the entire composite system, meaning the connector and the PCB effects together. We'll look at some analog system performance simulations in a couple slides. Give this guy 5 seconds to finish. And this brings us to the next section of this webinar, which is tying millimeter wave test and measurement tools, including simulation and testing, to a very current product trend, specifically the emerging landscape of small form factor 5G-enabled products. Hirose really does lead the CE industry in delivering micro board-to-board connector solutions for every flavor of these types of devices, again, from smartphones to wearables, smart home devices, etc. These small connectors are ideal for routing multiple signals, and engineers are now pushing to utilize the same type of small solution to route 5G analog signals, primarily from antennas or from antenna modules to modem chips, all of which would be embedded within the end product device. The best example of these types of products that I'm talking about for the board-to-board are the ones at the bottom. And just to show the size, here's a penny scaled up to roughly the correspondence of how this would actually appear. So these connectors are really quite small, down to 1.5 millimeters in total width, maybe 2.5 or 3, down to as small as 2.5 or 3 millimeters in total length. Taking those types of connectors and applying them to 5G RF signaling is a challenge. In 2018, we introduced our first RF analog optimized micro board-to-board solution for 5G, the BM46. This device has a total stack height of only 0.6 millimeters for both parts when they're mated. The pitch between contacts is only 0.35 millimeters, and the width of this device is only 2 millimeters end to end. This device was actually used by multiple OEMs in their first generation 5G CE products. It's rated up to 6 to 12 gigahertz performance. The connector design includes RF optimized contacts for better impedance control and resultant performance capabilities at those frequencies. Up to 12 gigahertz overlaps and covers not only the sub 6 gigahertz 5G band, but it can also work for a 5G millimeter wave configuration when that configuration is used with some frequency shifting or downstepping components, which is actually frequently the case for internal transmission schemes. The BM46 also includes a novel fully plastic insert mold embedded shield element between the two rows, specifically to optimize RF crosstalk or fixed next performance between RF signals on any upper and lower pins. Here's an actual simulation example of this device showing a representative RF analog transmission signal on a lower pin and showing the mitigation of that propagated noise to prevent interference with any associated RF signals or even digital signals that might be being transmitted on any of the upper rows. Now, in addition to the RF capabilities of the connector, it really does bring immediately an advantage in form factor to the product design as well. The layout and board space advantages are easy to see, where previously a combination of multiple micro coax lines plus another digital flex circuit can all be replaced by a single RF integrated micro board-to-board flex solution. To put this a little more clearly into perspective, here's simply two micro coax connectors spaced closely together on a PCB board. If these signals can be routed over contacts with a small micro board-to-board connector, the savings is immediately, easily 4-to-1 on that PCB circuit space. And in fact, that doesn't even take into account the fact that your two micro coax cables would likely still require an adjacent flex connector for routing digital and power associated with these transmission signal. All of this instead can be pinned out on the single micro board-to-board connector shown here on the right. So for consumer electronics devices, that's a big advantage, an important one. Since introducing this first 5G optimized part, our focus, together with many 5G product design customers, has begun to shift to two new areas. First, considerations of overall external emissions versus simply focusing on internal crosstalk, although crosstalk is still an important parameter on its own. And second, we're now developing solutions at Hirose to push the transmission frequency capabilities of these connectors all the way up to the true millimeter wave range of not only 30 gigahertz, but 40 and even 50 gigahertz to cover the primary millimeter wave 5G frequency bands being ramped up around the world. Our new BM56G represents a significant step in this new direction. This new series adds an aggressive new design to attack not only internal crosstalk, but external emissions mitigation through the integration of full 360-degree metal shields on both mating pieces. These structures are added directly into the plastic mold process through our proprietary insert mold technique, resulting in monolithic shielding structures which add a dramatic level of EMI protection in combination with optimized PCB and FPC cable designs. Through simulation and correlated with EMI lab measurements at our own facilities, it is seen here the level of mitigation of emitted radiation from internal RF signal pins to the external environment is reduced by orders of magnitude. Here is a representative image of a non-shielded board-to-board solution with optimized RF signal contacts, but with no mechanism designed into this to specifically address mitigating those external RF emissions that I just showed on the last page. And here is an even more generic but essentially accurate view of the type of shielding we're currently developing to add to these connector structures themselves. In this case, in the form of a directly embedded full 365-degree metal shield element on both the male and the female connector pieces. Some of engineers, I'll bet, have experience doing shield boxes around components or even combinations of components on a board. It's easy to imagine. This is essentially integrating the effect of having a shield box integrated into this tiny micro board-to-board connector to mitigate that power. Is a good way to sort of understand the analogy of what we're trying to accomplish here. And to do this and to look at these types of designs and optimize them takes us to a very different type of simulation environment versus the strict SI metrics such as VSWR. Instead, we now need a model of full far-field radiation fields. The optimization once again proves to be very sensitive to the full subsystem, not only individual components. The PCB, the connectors, and the FPC all must work together to achieve the level of noise integration that's needed. But after these factors are understood and optimized, the result is a dramatic decrease in overall radiated gain. On the left, the unshielded connector I showed has a scale that peaks at -37 dB, and the red shadings show that there is still radiation emanating from this structure near that peak value. On the right side, the shielded result is dramatically less emissive. Here, the scale peaks at a much lower value of -50 dB, and even within that, the yellow shading of the resultant model shows the actual radiation levels are nearer to the -50 to -60 dB. In summary, test and measurement solutions for millimeter wave domains are not new. But optimizing the performance of these solutions often requires not only precision, repeatable component performance, but also subsystem level analysis and optimization. At the same time, the emergence of 5G millimeter wave solutions in many product areas will continue to add importance to understanding these issues and finding optimized solutions for addressing routing of analog systems throughout these systems. Hirose brings a unique combination of strengths to these efforts, from our core millimeter wave test and measurement portfolio to our in-house signal integrity experience in modeling and simulating, not only at the component level, but at the system level, and working with customers to help bring our own designs to achieve optimal results. We've worked hand in hand with global leaders on enabling 5G solutions already, as well as with industry partners such as next generation FPC cable technology providers, and just as importantly with end customers, bringing those elements together in finished products. We look forward to hearing any challenging requirements you may have at any of these stages and working together to support you in your design and testing requirements. Thanks for your time today, and let me turn it back to Bill to wrap up and capture any questions. Bill?
Great. Thank you, Mark. And Kim, if we can get it back to the overall view.
I think Mark has to stop sharing.
Ah,
Okay, that I can do. There you go.
great. And so we'd like to open it up for questions. If you'd like to ask a question, please enter it in the chat section of this website. So let's see if we've got anything in there yet. So, Mark, we've had one here that is someone is asking us if they can have the VIA optimization PDF file. Is that possible to share with the customer?
Most likely, yes. So we need to understand exactly what they're looking for. And so I would suggest that if they've already submitted that question, if they include their name or resubmit another, repeat that question with their name. I think, Bill, we've got their email addresses from the webinar, so we could follow up directly with this individual and make sure we can address their question. But yes, VIA optimization and PDF files or even CAD files of those types of optimizations are something that we generally are happy to provide and work with a customer on.
Great. Okay. And I do have their contact information here, so we'll be able to take care of them. Then I have another question. Any release dates for the RF board-to-board connector series? They don't mention a specific series, but RF board-to-board.
No, that's a good question, and one we're excited to look forward to. It should be later this year, and actually we are in a stage where if we can vet your project, at least as being something that looks like it's real, and I'm sure it is. We actually have samples of some of these connectors already in hand here in the United States, and definitely a lot of information, including test data on these connectors. So they are actually very close to being released. So the answer is yes. We could definitely support you on that. We could definitely get you more information on those on a one-by-one basis, and those should be becoming available for volume production capabilities within this year. So please follow up with us if you have an application where these might be of interest. We'd love to learn about that and share with you more details and even get you started with some samples very soon.
Great. And Mark, and I've got a follow-up from this person that is asking for 5G TXRRU units that had to do with that same RF board-to-board connector.
Well, yeah, TXRX, if he's talking about a test board, perhaps, that's something that we already actually have spun for those devices. I'm not sure I understand exactly what he's talking about, TXRX unit, but I'm guessing he or she might be asking about a test board type of solution. Absolutely something we would be able to put in somebody's hands with a test FPC, length of straight cabling between two different devices. So it sort of looked like the little models that I was showing on some of my slides, which is a good subsystem type of starting point for looking at how performance is going to be on these.
Great. Okay. Then I have another question from someone else that said, did you say that hardware comes with the 2.92 and 1.85 millimeter connectors?
Well, the connectors, yeah, our connector is the hardware that we deliver. So we don't, in fact, it's shown here, the second to the right picture, right? The metallized connector is the hardware that you would find from Hirose. As far as, again, if you're talking about the PC board element, we do have test boards available for these devices as well. You need to, again, follow up with us directly. We may not have those available from a distribution, online site, for example, but it's something that we can definitely support you on. If you're talking about cabling or some other element of hardware, we might need your help to understand exactly what you're looking for. But I hope that answers your question. The metallized connector is the Hirose part. We definitely can support you with some test board environments and cables as well.
Yeah, actually, there's a follow-up to this as you were talking, and he asked, no, specifically mounting screws and washers.
Oh, absolutely, yeah, the mounting screws. We don't provide washers, and our customers in generally don't. The actual hole, the flanges on the sides of the connector are threaded holes, and so the mounting scheme is to thread or to insert a screw through clear bored holes through the bottom side, if you will, of the PCB and thread those directly into our connector. We don't require washers, but we do include, and as I said, the suffixes on our part numbers, there's an 11 and a 12 suffix, or there's a 15 and a 16, and those refer to the length of the machine screws. So you can, and that might depend on the thickness of your PCB, of course, that you choose from those. But washers can certainly be utilized at the customer's discretion as well. And so the answer is yes, the screw mechanisms are available. Make sure you order the part that has the suffix with an 11 or 12 or a 15 or 16. If there's no suffix at the end of the part number, that means no mounting screws are coming with the part.
Yeah, I think we offer them both ways, with and without the mounting screws, if you choose. Okay. Then I've got another question here that says, how do you shield structures? How do shielded structures keep noise from leaking since the top and the bottom of the connectors are open?
Okay, that's a good question. And I think that's referring back to our micro board-to-board connectors in this case, where I showed the picture of the 360 degree shield. And so that you're right, the top and bottom, and that goes back to the fact that it's all about the system, and it's, forget the individual component, which what we've learned in the last 3 years of working with 5G OEMs is for these high frequencies, you really need to optimize the full subsystem. In this case, the top and bottom would be, on one case, the PCB design, where you are going to have a very sophisticated ground via patterning and optimization. You may have additional layers and additional elements embedded in your PCB specifically to mitigate the emission of that high frequency RF. So that would be effectively the bottom of this box that we're talking about, that our 360 device shield is the walls of. The top of that box would be the most typically an FPC device. And as I said, the FPC manufacturers are also ramping up their technology to increase the radiation mitigation aspect of their devices. And that might also include something like ground stitching along the edges of the FPC, additional ground plane layers on the FPC itself, or even additional materials attached to the surface of the FPC. So the FPC and the PCB would essentially be the top and the bottom. But it's a good question, because you're right. Our shield is simply, if you will, the walls between those two elements. But it all has to work together. And that's where we've spent a lot of time in doing the simulation and modeling to optimize that with partners at both of those stages. Great.
Thank you, Mark. And then I've got another question that I'll answer. It was from the person who earlier asked about the RF board-to-board connectors. Simply stated that they're from India. And I think that would be not a problem having someone from our sales organization contact them in India. No problem at all. Absolutely. And just see, we might have one more here. The question is, where can they get specific help on millimeter wave solutions for modeling in their design, both test and measurement and small board-to-board applications? Okay, well, we do right from our public website. You can go to some of these series and you can find 2D and 3D IGES and STEP 3D models available. You may need to register for free. It takes about 3 minutes, I think, on the website. And there's even HFSS models, which aren't available publicly on the website. But again, if you contact us, we can talk to you and give you some at least black box HFSS models if needed for doing further simulation on your own of these connectors in a larger system. So take a look at the website. You can our website's pretty easy to use. Go to hirose.com. You can put in HV, to start some of our series, or even you could put in millimeter wave probably and start to find the right parts. You'll be able to find some 2D and 3D models, and get in touch with us if you're not finding exactly what you want. I think we do a really good job of being able to support you on those engineering questions. And again, we've got our team right here in San Jose to help out. Great, thanks, Mark. And I think that might be about it for questions. I don't see any more coming in. So maybe we can wrap it up here. Thank you all for joining us today. Hope this webinar was informative and you gained some ideas to help you with your millimeter wave applications. If you would like us to contact you directly, please enter your contact information in the chat section, and we'll have a salesperson or a sales engineer get in touch with you and see if we can help you with that. And for more information, please visit us at www.arose.com. And don't forget to follow us on LinkedIn. So good day and stay safe. Again, thanks for coming. Bye-bye.